Caught it early before I went to slide 2. Hi, for those of you just joining this recording, I haven't said much yet, but this is week 2 of QDA, and we're going to talk about the scientific method. So if you've had me in any classes this year, including UXT or this class, you will have already seen my obsession with this wheel diagram for the scientific method. If you take research methods next term, I suspect I'll be teaching that, and I suspect I'll be using this diagram again. I really think this underlies everything that you'll be working on for your degree, no matter what your degree is in. If you're in this class, you're doing science, so the scientific method is vital to what you're doing. Likewise, if you're in a degree that's asking you to take this class, knowing this process and being comfortable with this being a circular process that feeds onto itself is something that'll be useful for you to remember throughout your career. Today, we're going to focus on, and throughout QDA, we're going to focus on the kind of 3 parts of that wheel that are on the right: the hypothesis, the experiment, and the analysis. Different modules you take might focus on other steps of that wheel, but this class focuses on those 3. The first step of those 3 components of the scientific method is generating a hypothesis. So a hypothesis is not merely a random guess or just a prediction about the world. It is specifically a testable statement that can be either supported or rejected. In order to evaluate a hypothesis, we design a study. Sometimes that's an experiment, or sometimes it's an observational or cross-sectional study. And either of those types of studies, either an experiment or a cross-sectional study, help us test that hypothesis. And we'll get into the details of those 2 types of studies as we carry on this lecture. After we've designed our study, we can use that study design to collect data. We get people to come experience our study. We get observations from people that make up our data set. We'll talk about how we decide who those people are, how we get them to experience our study, and how we make sure that our experiment or our cross-sectional study is appropriate for our hypothesis. Once we have people go through our study, once we've generated our data, now we have data and we need to model it. We need to use statistics to model the data. That is to say, we choose a statistical test that helps us identify important trends in our study that would help us evaluate our hypothesis. Finally, after we've fit that model, after we've used a statistical test to compare what our hypothesis predicts to what the data actually says, we can evaluate how well that fits. We can evaluate whether our hypothesis is supported or rejected. This is where we decide whether that evidence is enough to support our hypothesis, whether that evidence is not enough and we should reject our hypothesis. And I just wanted to quickly note, Ben noted this last year and it was a big hit, so maybe this will get people fired up, but this idea of fitting models to data and then assessing the fit of those models is exactly the same scientific process, exactly the same philosophy that underlies artificial intelligence, that underlies machine learning. So the tools that we use to do scientific research, what we cover in this class, are conceptually the same exact tools that underlie a lot of the technology we interact with all the time. We have different aims than machine learning. In this class, we're testing hypotheses, we're doing the scientific method, we're completing the wheel. Machine learning might be more about an output than testing a hypothesis, but it's the same exact process of trying to gather data and fit a model to that data and assess how well that model fits. So let's take these steps on the right, one step at a time, and first talk about how we generate hypotheses. Hypotheses can be formed in either of 2 ways. As the circle diagram implies, one route for generating a hypothesis is just making observations about the world that cause you to ask questions about what you're observing. So one example that I like to use, because my research is kind of in this area, but also because it's pretty true to life, is the example of the phenomenon texting while driving. Something that if you're riding your bike or walking or driving around Dublin roads, you're almost sure to see. I know when I'm perilously trying to cross the N11 to get from UCD to Sydney Parade, inevitably you'll see people, especially at a light, trying to fire off a rapid text message before the light turns green, or maybe while the light is green and they're actively driving. So let's pretend that I'm perilously crossing the N11 and I notice that a driver is sitting at a red light texting and they fail to react to the light turning green because the driver's looking at his phone. This might lead me to observe that that driver had a slow reaction time. And maybe I could theorize that the driver's reaction time was slow because the phone was lowering the amount of attention that he put on his driving. And this is what caused that reaction. In this way, I'm beginning to form a hypothesis. I'm coming up with an explanation for behavior that I observed in the world, and I'm coming up with an explanation that can be tested, something that I can use to predict some other behavior, see if that behavior occurs, and evaluate whether that hypothesis was any good or not. Alternatively, hypotheses could also be generated based on existing theories about the world that have been developed from other hypotheses and studies, so the circle feeds itself. You might, instead of observing someone texting and driving on the N11, just know something about cognitive science and know something about cognitive theories like multiple resources theory. So that theory, you don't have to know it. It's not part of this class in any way, but multiple resources theory says that tasks that overlap in the resources that they demand are more likely to interfere with performance of one another. So this theory could make me think, driving and texting both demand a lot of the same resources. They both demand visual attention. They both demand some sort of manual response. So you have to interact using your hands. They both require some planning. They both require some decision-making. They overlap a lot. So I would predict based on that theory that texting is detrimental to driving. Now, multiple resources theory doesn't specifically talk about texting and driving. And I don't need to have been wandering on the N11 observing texting and driving to make this prediction. But purely from this theory itself, I could come up with just the same sort of hypothesis that I would have come up with by observing the world around me. So that's all just to demonstrate that hypotheses can come from either direction. They can come from observations that you make, or they can come from other theory, other research, and you can arrive at just the same hypotheses either way. So that's kind of the rough idea of a hypothesis, and I'm going to put the specifics of formulating a hypothesis on hold for just a minute, and we'll come back to them. But first, I wanted to return to that question of what types of studies are, what the difference between a cross-sectional study and an experiment are. So in this class, these are the two major options we talk about. It's maybe not quite so cut and dry that there are just two options and it's either one or the other, but for the purposes of this class, we'll talk about it as if these are the two types of studies that you might run. When we design a research study, we could, on the one hand, choose a cross-sectional study. That means we're getting a cross-section of the world as it exists. We're slicing the world on the axis of time, right? We're taking a snapshot of the world as it exists in a moment and describing that moment. To keep up that texting and driving metaphor, it might be like if I stood on the corner of the N11 and set up a camera and recorded drivers' behaviors for a few hours. I'm not altering anything about the world. I'm just observing the world exactly as it exists. I didn't like alter variables. I didn't form some control group or anything like that. That has a benefit. That means the study is highly ecologically valid. It's very much like the real world. I didn't alter anything about the world. In fact, what I'm observing is the real world in a sense. Since I don't have any control of the data I collected, however, I don't have the ability to make causal conclusions about it. That is to say, I can't say that one thing caused another thing to happen because there's just a lot of noise. There's a lot of other confounding variables. I might record all that data and find a bunch of people who are texting and driving, see that they had really slow reaction times, but I might find that they were also drinking and driving at the same time. That means even if I found that these texters were worse drivers, I wouldn't know that they were worse because of the texting. Some third variable, some confound crept into my study. That's why we can't use cross-sectional studies to make claims about cause. There are these third variables, these confounds that make that an impossible relationship to verify. We can, however, comment on relationships existing between those variables. We can say that the amount of time spent texting correlated with quality of driving in a negative way. We can't say that the texting caused the poor driving. Something else might have caused both, like maybe age or experience with driving or something else, but we can say that they're related. If you put a camera beside the road to watch drivers text, would they be more likely to alter their actions because of the presence of the camera? Absolutely, yeah. So I didn't necessarily specify, is this like a little camera hidden in a tree that no one will possibly see? Is this like a big public camera with signs saying like you're being recorded? But that's why I kind of shied away from saying it's perfectly ecologically valid. It's not. It might be highly ecologically valid. It might be concealed in such a way that I didn't alter the world much, or it might be less so. It might be a big obvious camera that everyone knows is there and changes the way they're behaving. This is going to be true for all cross-sectional studies, that there's always a spectrum of how much ecological validity you maintain and how much you're altering the world. But you're right, in general in science, there is this principle that we do change, we change the world, we change what we're observing by observing it. So that's a very good point. On this concept of third variables and confounds, I'm about to out myself as a giant boomer who's trying to be really cringe by appealing to the kids, in that I thought of a TikTok sound that perfectly explains why third variables or confounds are bad for experiments, and this is it.
I can't believe that it's finally me and you and you and me, just us and your friend Steve. Do Steve. Do.
So third variables are like Steve. You want your main variables of interest, the things that are in your hypothesis, me and you and me, to be on their own if you're going to make causal claims about them. Third variables, confounds, are Steve. They ruin that relationship, so you cannot make causal claims. And that's exactly why we might design an experiment instead. Experimental research means we have direct control of a variable. Rather than observing the world exactly as it is, we build a contrived experiment just to make sure we have a different version of that scenario that we can control. Yes, my apologies to the Steves in class. I know we have at least 2 people actually named Steve and many people who are saying, I am Steve. Like, yeah, I feel you. I've been the Steve in many social circles before. So yeah, we might design an experiment to look at the relationship between texting and driving rather than using a cross-sectional study. So instead of hanging out at the N11 all day or setting up a camera, maybe I get permission from UCD to use their parking lots as driving test tracks. In my experience, UCD would probably not say yes to that proposal, but let's say that they did. In this case, I would get a bunch of people. These are my participants in my experiment, and I would then assign them to conditions. I would get to control whether they were texting and driving or just driving and not texting. In this way, the experiment has a lot less ecological validity. It's less like real life for a number of reasons. I'm on a test track. People are told to text and drive, or told you're not allowed to text while you're driving. But on the other hand, I have much greater control of my variables. I now know exactly why people are texting or not texting. It's because I told them text or I told them don't text. And as long as I make everything else the same between the 2 conditions, I know that the only thing different between the 2 conditions is the presence of texting or the absence of it. That way, if I do notice some difference between driving abilities, I can make causal claims. I can say that that difference was caused by texting. I can say texting leads to worse reaction times while driving or something like that. And I can only do that because I had control, because I controlled one of the variables. Causal claims like this are only possible when we run experiments. Now, this relates to the comment a bit earlier from Megan, but in reality, there isn't a sharp line between cross-sectional studies and experimental research. It's not that some studies are experiments, some are cross-sectional and there's nothing in between, or that some studies are completely ecologically valid and some are completely contrived and there's nothing in between. In reality, it's more of a continuum between control and ecological validity, that as you get more of one, you typically get less of the other. If you end up taking research methods at module in the spring, this is a point I will return to frequently if I'm teaching it, and if I'm not, whoever is will make that point as well, that you always have this, this trade-off between control and ecological validity. So that is my same slide again. I hope I didn't lose a slide there. So let's talk about an example experiment. Yeah, so let me go back to that idea of ecological validity. So my cross-sectional study has high ecological validity. all ecological validity means is similarity to the real world. It's valid in that it's similar to the actual phenomenon I'm trying to describe. So setting up a camera on the N11 to get texting and driving behavior, that's highly ecologically valid because I'm just recording the real world. I'm getting evidence of something that's really happening. As Megan pointed out, I might sacrifice a little ecological validity. I might make it less like the real world if I make my camera really obvious, for example, or if we give warnings on the radio for a couple of days in advance that like on the N11 at 4 p.m. there will be a UCD student recording whether you're texting and driving. Things like that are altering the world, so they're making it less like it normally would have been otherwise. That's the idea of ecological validity. If something is extremely like the real phenomenon, then it's ecologically valid. The less like the real phenomenon, the more contrived, the more designed it is, that's less ecologically valid, but typically more controlled. So let's talk about this example experiment some more. So let's stick with that idea for this week. We're going to use the example of an experiment rather than a cross-sectional study. I would say in general, most weeks we will use an example experiment. Some weeks we might use an example study, depending on what statistical analysis we want to use. So depending on which statistical test I'm teaching about, I'll tell you whether we have a cross-sectional design or an experiment. In reality, that works in reverse. You'll come up with an experiment or a cross-sectional study, and then you'll decide which statistical analysis is appropriate. But for our purposes, let's stick with the idea of an experiment for now. So for that example, yeah, I'll just say clearly once again that we're imagining an experiment where we want to learn more about texting and driving. UCD decided for some reason that they're wheeling out the money for me. They're backing up the money truck to my house. They said, you can use all of our big parking lots as your test track. You can have this test car that all of your participants can drive in. We'll help you set up some fake traffic lights around campus, anything you need. So I set all that up. I set up some fake lanes and traffic lights. And now I can bring participants into my new lab, my experimental setup, and ask them to do some texting and driving, or ask them to do some driving without the texting. And I am representing this by this, I wouldn't call it even photoshopped, but this poorly cropped and overlaid image of a race car driver with a phone. Yeah, so that's the example experiment we'll be working off of for the rest of today's lecture. So just pretend we're at UCD. We have a bunch of people who are either going to be texting and driving or just driving around and not texting. So I need to formulate a hypothesis about what I expect to happen here, what I'm trying to measure. So like I said, I observed somebody at a red light, it changed to green, and they were too busy texting that they didn't react to the light very quickly. Therefore, my hypothesis is going to somehow relate the variable of texting or not texting to the variable of reaction times. So I want to take a moment to quickly explain dependent and independent variables. This is the idea of when you have an experiment that one of your variables is the thing that you control and the other variable is the thing that you are measuring. So in an experiment, we systematically manipulate one variable, and that variable is called our independent variable. What makes it independent? Why is it called the independent variable? Well, we know that nothing else impacted that variable. Nothing else influenced somebody's reading, somebody's value or score for that variable other than us. We, the experimenters, set that variable for them. It's independent of all outside factors. In this case, texting or not texting is our independent variable because we're telling people you're texting while driving, you're not texting while driving, or something like that. That makes it an independent variable. Nothing else influenced it other than the experimenter. The variable we're measuring, on the other hand, is the dependent variable. Our hypothesis said that the other variable we're interested in is reaction time. That's what we're going to be measuring. So if our hypothesis is that texting causes reaction time to change, the variable we're measuring, dependent variable is reaction time. Why is it dependent? because our hypothesis is that the value for that variable, someone's reaction time, depends on the condition of their independent variable, that we can use their independent variable, texting or not texting, to make some kind of prediction about their dependent variable reaction time. And again, this differentiation, this independent variable versus dependent variable thing, only applies for experiments. So if we have an experiment and we're controlling something, we have an independent variable, therefore we have a dependent variable. On the other hand, if we're doing a cross-sectional study, we're not controlling anything. We don't have independent variables. We don't have dependent variables. We just have variables in a cross-sectional study. DV is the dependent variable. It depends on the value of the IV, the independent variable. I just want to read Paula's comment real quick. In the social sciences, designing experiments where you can control everything is difficult. Absolutely. And we'll get back to that topic too, that no matter what, you're always at the risk of confounds. You just need to be aware of what confounds you might be at risk of introducing into your study and how dangerous they are to your hypothesis. We'll talk more about that at the end of this lecture. And we'll also, again, if you take research methods in the spring, that's like a huge part of that class. But Paula's absolutely right that in the social sciences, you're almost never going to be able to isolate all variables. When I say that we're isolating everything but the independent variable, I'm being a little overconfident in my ability as a scientist to do that. But that's the story we tell ourselves anyway. We're trying to systematically manipulate one variable and make all other variables as constant as they can be. So let's talk about the variables we have in our experiment. If the variable we want to control is the secondary driving task, so whether or not someone is texting and driving, that is our independent variable. For this independent variable, we'll have two conditions, or you'll sometimes see them referred to as levels, or in the physical sciences and like medicine, you'll see this referred to as treatments. But we'll stick with conditions for now. We have two conditions to our independent variable of secondary tasks. One condition is our control condition. So people in this condition are not texting, they're just driving. This is kind of the baseline against which we compare our experimental condition. So our control condition, just driving, no texting at all. And then our experimental condition, driving and texting. So for this variable for secondary task, the control condition, there is no secondary task. The experimental condition, there is a secondary task, it is texting. Our dependent variable, the variable we're interested in measuring, in this case, we're sticking with reaction time. So I might measure that by how long after the light turns green does a driver take to press down on the accelerator? Or maybe I design my course, my racetrack in such a way that it's how long did it take for the driver to hit the brakes before my research assistant jumped into the middle of the road? UCD probably would not give me permission for that study. We could have used any number of other variables as our dependent variable here, like how well did drivers stay in their lane, or how well did, how good was their driving if a judge rated it on a scale of 1 to 10. You could use any different variable here. You could operationalize that driving ability in any other different way. But for our purposes, we'll stick with reaction time measured in milliseconds, and we'll pretend it's reaction time from the moment that the light turns green to the moment their foot starts pressing on the gas. On the accelerator. I think pressing on the gas might be a pretty American way of saying that. This is meant to be an Irish education, damn it. I didn't pay for this, American. So yeah, now we have a good idea for our research design. We have a good idea of what our variables are. Let's talk about how to state a hypothesis. So I want to start by doing this in inverse order. So instead of talking about how exactly a scientific hypothesis should look, let's talk about some ways a hypothesis might look unscientific. A hypothesis, first of all, must be testable. It must specify some variable that is possible to measure. My first crack at a hypothesis here isn't very good because I can't test the statement drivers who text are evil because I don't have any good way of measuring evilness. This variable doesn't really lend itself to a scientific study or to a scientific hypothesis. Next, a scientific hypothesis must be specific. So in the second attempt at a hypothesis, drivers who text are worse at driving than drivers who don't text. it's just a bit too vague. Sure, you can measure driving quality with any number of variables, like I just said, but this hypothesis does not make any specific prediction about the way a driver who is texting will behave as compared to how a driver who is not texting will behave. Like, there's plenty of ways that they won't be worse. They won't be worse at like sitting in the driver's seat. They won't be worse at remaining awake. So because that hypothesis is so vague, it might not be clear to me if my evidence is supporting or rejecting that hypothesis. Next, a hypothesis ought to be parsimonious. That is to say, it should be simple, stated as simply as possible. This third hypothesis, drivers of white Audis on the N11 who text are exactly 21.6 less fast at reacting to red lights than all other drivers, is needlessly complex, is overly complex. It's making predictions about components that we're not all that interested in specifying. We don't really care that this is specific to the N11 or that this is specific to white Audis or anything like that. We probably don't even care that it's specifically 21.6% less fast. This hypothesis is unnecessarily complex, so it violates our desire for a scientific hypothesis to be parsimonious, to be simple. Finally, a hypothesis must be falsifiable. It must be stated in a way that there's some possible evidence we could get that could be used to reject that hypothesis. So my fourth attempt at a hypothesis here, my fourth bad attempt, is drivers who text have low reaction times. Now, this, you might also argue this is vague or that this is untestable. I would say that the problem with that statement is it's not falsifiable. It's not clear to me what evidence I could get that disproves that. How fast would someone's reaction time, how fast would all of my participants' reaction times have to be for me to say, okay, I was wrong, drivers don't have low reaction times? Or even how slow could they be for me to think that I was right? This is not a falsifiable statement because it's not making a specific enough prediction. What we want our hypothesis to be is testable, specific, parsimonious, and falsifiable. So those are kind of the opposite words of the words I just gave you. Parsimonious, again, just means simple. It's, Occam's razor, the simplest solution is the best solution. With those guidelines in mind, here is my attempt at a hypothesis for this experiment. There will be a significant difference between secondary driving tasks on reaction time. So I'm specifying it in terms of my independent variable and my dependent variable. And when I say significant difference here, I'm not making any claim about how big that difference will be. In terms of a scientific hypothesis, significant just means that I'll be confident that the difference exists at all, that the difference is not zero. As we get further into this class, I believe next week, I will go into some more explanation about how we measure our level of confidence, how we measure our level of significance for a finding. But for now, let's kind of bracket that and just say that all I'm meaning to say here is I will be confident that there is a difference between secondary driving tasks in terms of reaction time. This hypothesis is now testable, specific, parsimonious, and falsifiable. But falsifying this hypothesis is not really what we're looking to do, right? This is the hypothesis we think is right. So falsifying it would be, it would kind of be a waste of our time. We ended up finding that our hypothesis was wrong, but how would we know that our hypothesis was right? In order to do that, we have to actually also specify the opposite of our hypothesis. We have to specify a null hypothesis that we hope to falsify. This null hypothesis is an inversely stated version of our research hypothesis. This is, in this case, there will be no significant difference between secondary driving tasks on reaction time. This is necessary because of how statistics work. Rather than proving that something is true, all our statistical tests have the power to do is reject something, is to falsify something, to give evidence that it's not true. We therefore implicitly always, when we use inferential statistics, are trying to test whether our null hypothesis fits the data, rather than testing whether our research hypothesis fits the data. If we reject the null hypothesis, we can therefore say that our research hypothesis is supported. Now, in written reports and scientific papers, people normally don't write out their null hypothesis like this. It's not normally stated explicitly. It's just implicitly kind of baked into the statistical tests that we use. Since we are learning statistical tests in this class, we will talk about null hypothesis. We'll make null hypotheses explicit. That said, it's always important to consider what our null hypothesis is when we perform a statistical test, because this is the actual hypothesis that the test is testing in almost every case. So why do we need to falsify the null hypothesis rather than just proving the hypothesis? Why do we do this little statistical trick, this trick of falsifying the opposite instead of proving the positive version? This is the idea of null hypothesis significance testing. This is the philosophy that underlies most of modern statistics, all of the statistics we use in this course. And this springs from the idea of parsimony, of simplicity, once again. The idea that using the simplest model for describing the world is better than using an overly complex model. So rather than assuming that every new hypothesis that pops into my head is true, well, that's normally the case because I'm really good at thinking. No, rather than assuming that every new hypothesis that pops into my head is a true statement of fact, a true description of the world, I instead have to assume that every hypothesis that pops into my head is wrong, that every null hypothesis is true, and that only overwhelming evidence would cause me to think that the hypothesis that popped into my head, my research hypothesis, is true. That's because it's easier to describe the world without these new hypotheses. It's simplest to describe a world where there isn't any relationship between texting and driving or between any other set of variables. It's simplest to assume a state of the world where none of that exists and all of our nulls are true. In order to adopt a more complex view of the world, in order to complicate our view of the world by adding new hypotheses to it, we need overwhelming evidence that makes us very confident that our null hypothesis was wrong. Next week and beyond, again, I'll be talking more about how we measure that level of confidence, that level of significance. But for now, I'm simply going to put it in that term in terms of confidence. So we use null hypothesis significance testing. We test against the null because we always assume that the null is right. It's simplest to just assume that the world doesn't have any of these complex relationships, that our hypotheses are wrong. And it would take a lot of evidence to change that simple view of the world, because a simple view is easy, because a simple view is the best. So we have our hypothesis, we have an idea for our experiment. Now we just need to make a choice about how exactly we design the experiment. We have two options for how we want our conditions to work. Either we can let every single participant that comes into our lab or comes to my test track experience just one condition. That would be, they only experience one condition of the independent variable. They're either texting or they're driving. Or we can make every single participant experience both conditions, that everyone who comes to the lab will experience the entire experiment in the texting condition, and they'll experience the entire condition in the no texting condition. If we choose that first option, we have different participants in each condition. So I've visualized this by having our race car driver with a phone again.
Each participant only takes.
Oh, sorry. I unmuted you by instinct as soon as I heard someone talking. You can unmute and ask me the question. Sorry. Yeah, go ahead. Oh, never mind. I will go ahead. Yeah, so I wanted to demonstrate this idea of a between subjects experiment with my race car driver with a phone and my even more handsome race car driver with no phone. So there's the idea that different people are in different conditions. We're going to be comparing dependent variable measurement between subjects in one condition and subjects in the other condition. So we're going to be comparing reaction times of the people who were in the texting condition against reaction times of people who were in the no texting condition. This approach does have some benefits. So first of all, for my participants, this will take them less time. It's easier to recruit participants to do, let's say I want them to drive around the track for 1 hour in either condition. It's a lot easier to convince like your friend or to convince some stranger to do your study that lasts 1 hour than it is to convince them to do the study that lasts 2 hours if they had to experience both conditions. So for practicality's sake, sometimes it's easier to recruit if you use a between subjects condition, because theoretically it cuts the amount of time the experiment takes in half. It also has some other benefits. So if if I asked people to experience both conditions, if I did that thing where I had them do the texting and driving and then had them drive without texting, that also introduces practice effects. That is, if I asked you to drive around the track once and then drive around the same track again, even if it was in a different condition, you're probably going to get a bit better at driving on the track the second time because you've experienced it once, because you've practiced it. By using different participants for each condition, nobody gets any practice. We know that practice is not influencing our measurement of reaction time or of however else we're measuring driver quality. Sorry, on the one hand, on the other hand, this might introduce some negative confounds as well. So let's say my handsome driver, my Justin driver, is way better at driving than that race car driver guy. And texting doesn't impact anything at all. Let's say the texting doesn't impact your reaction time. There was no relationship there. But Justin's just such a good driver compared to that race car driver guy that his reaction times are off the charts, that it just seems like that, yeah, Justin's driving is so much better. Now, even without knowing anything about texting and driving, because they have such a difference in skill in driving and because they have such a difference in skill in reaction time in this example, now I don't know if the differences we observe between participants in reaction time is because the participants naturally had differences, they just had individual differences between them, or if that difference was because of my independent variable, my texting condition. Likewise, if it was the other way around, maybe my texting and driving guy is way better at driving than I am, or that this handsome race car driver is. If that's the case, then even if there was going to be some difference, even if his reaction time was slowed down a lot by texting, he's just such a better driver that he masks that effect altogether. I don't even get to see the difference between conditions, even though I should have, because of this natural variation. In this way, between subjects conditions allows for individual differences to become third variables. It allows them to become confounds. It allows them to become Steve. And we don't want that. That's a way to introduce confounds. Now, of course, with more than just these two participants, if we had 5 or 10 or 50 or 500 participants, we would hope that these individual differences cancel out. They balance each other out. We might also choose some way of sampling people and assigning them to conditions to make sure they balance out. We might ask everyone to tell us, before we assign them to a condition, tell me how long you've been driving when you sign up for the test. That way we can make sure that the two samples are matched for experience in driving, or we can ask people, tell us about, how great of a texter and driver you are, or something like that. We can sample match to make sure our between subjects conditions have roughly similar samples of people in whatever confound, in whatever individual difference we're worried about. On the other hand, we could do a within subjects experiment. So the alternative to between subjects is within subjects. Every participant experiences every condition of our independent variable, and we measure the dependent variable as it varied within each individual. I'm not comparing one person's score to anyone else. I'm only comparing one person's score or one person's value for that dependent variable to their own score in the other condition. So again, using our race car driver example, this is like having the same guy, the same race car driver, run the whole experiment through while texting, and also run the whole experiment through our course while not texting. He experiences both the texting condition and the control condition if it's a within subjects design. Within subjects designs also have a number of benefits and drawbacks. So first, the kind of practical recruitment idea. If you have a within subjects experiment, you don't need as many participants to get the same number of observations. Let's say we decided ahead of time we wanted 40 data points. If we wanted 40 data points in a between subjects experiment, we would have needed 40 participants, 20 who did the, if we wanted to compare, I'm getting ahead of myself. If we wanted to compare 40 data points in the driving condition against 40 data points in the control condition, We know we want 40 data points in both conditions. If we do that between subjects, that means 80 people because there's 40 people and 40 people. But if we do a within subject experiment, we have 40 data points total. That can all just come from 40 people. You have to recruit half as many people to get the same numbers of data points in a within subjects design. That's kind of the practical benefit to doing within subjects. In terms of confounds, it has the benefit of eliminating individual differences between subjects. Participants' measures for the dependent variables are only being compared against themselves, not against other people. So if we think that every individual varies a lot and that it's going to be hard to make our samples match in terms of those individual differences, then a within subjects design can help because now we don't need to worry about them at all. On the other hand, within subjects designs has that idea of practice effects that I just mentioned. My driver gets to drive the same track twice. So the second time around, they're probably going to be a better driver. Or for other experiments, we might worry about people getting bored. If you had a really long, boring experiment, don't worry, all of my experiments are long and boring, so you wouldn't be the first person in this school to run an experiment like that. But if your experiment's really long and boring, the second time around, if people do that long, boring experiment again, they'll probably get worse at doing it, have less effort in doing it because they're just so bored. In this case, a within subjects design makes it a bit harder. In this way that either practice effects or boredom effects become a confounding variable, a third variable, and I won't play the Steve sound again. Which way can lead to better experimental results? Will this depend on the hypothesis we're experimenting on? Yes, so that's going to be a big focus again in the research methods module. Both have positives and negatives. I've introduced them in some brief way, but it's really going to come down to what exactly you're studying. Some studies will only lend themselves to one or the other. For example, if there's like a big surprise, like if let's say your experiment is measuring like how scared people get when you jump out from behind a wall, that would pretty much have to be a between subjects experiment because once the surprise happens once, it's not going to be surprising the second time. There's a handful of different considerations like that might make it so only one or the other design is better for you. We'll cover that a lot more in research methods, though. It's a little bit outside the scope of QDA, but you're right to say it depends on your hypothesis and it depends on the phenomenon that you're interested in. I also wanted to say that practice and boredom effects can be mitigated within subjects design by counterbalancing the order in which participants experience those conditions. So for half of my participants in a within subjects design, I would have them do the control condition first and then the texting condition. For the other half of my participants, I would have them do the texting condition first and then the control condition. That's one way to help mitigate your confound, but as Paula pointed out, when we're doing social science, we're never going to completely chase those confounds out. It's just something you kind of have to live with and try to minimize as much as you can. And again, we'll talk more if you take research methods, really going hard for that class. You'll get a much better coverage of that. This was just to differentiate for the purposes of our statistical tests. Sometimes we're using between subjects tests, we're comparing between different people. And sometimes we're using within subjects tests. We're comparing someone's own scores or values or measurements against themselves. So now we have some idea of where all of our data is coming from. We have an idea of what our hypothesis is, but what does that data look like? So I'll quickly go through that. We have 4 types of data that we might measure. The first type or level of measurement is called nominal data. Nominal data is the form of categories that don't have any order. Things like which condition you were assigned to, so texting or control. There's no order. It's not like one is bigger or better than the other. Other categorical variables, nominal variables like gender, occupation, might likewise be considered nominal. For nominal variables like this, it makes no sense to compare sizes or amounts. I can't say that one participant had a higher level of gender than another participant or a higher level of which condition I assigned them to for the experiment. Next, we have ordinal data. Ordinal data is kind of the next next level of measurement that lets us do a little bit more statistics. Ordinal data is categories, but now categories which are ranked, which are ordered. This might be something like which position someone finished in a race, first, second, third, or gold, silver, bronze, or how they describe their level of experience with an app. Beginner, experienced, expert, something like that. I can say that an expert knows more than a beginner, or that a gold medalist finished ahead of a silver medalist, but I don't know that the differences between each rank are the same. I can't say that the gold medal race winner was the same amount faster than silver as silver was than bronze. I just don't know what the actual difference was between them. In this case, it doesn't make sense for me to comment on the average level of something like experience. I can't say that we had the average app user in my study was expert 0.5 or something. Like I can't use multiplication or averages when I'm talking about ordinal data. Next up, we have interval data. So this is where we start working with actual numbers that we can add together. Most dependent variables that we deal with in this class are interval or ratio data. They're either of this or the next level of measurement. Interval data is any data with equal intervals between the numbers, but no true zero. So things that are interval data might include Celsius temperature or IQ scores or ratings on a Likert scale, where it's like on a 1 to 7 scale, where 1 is highly agree and 7 is highly disagree. Those are all interval scales. They lend themselves to addition and subtraction. We can use statistics like averages now. We can use standard deviations. But because there's no zero, we can't use multiplication. And to quickly demonstrate that, it wouldn't make any sense for me to say that a 4-degree day is twice as warm as a 2-degree day, because how much warmer is that than a negative 2-degree day, right? It's like, it's infinity% warmer today than it was yesterday. It doesn't work because there's no zero to speak of. Finally, ratio data is data where we do have a true zero. So this would be things like reaction time or height, distance, where you can have zero as a measurement, but you can't have anything below that. We can do things like means and standard deviations, but now we can also do multiplication comparisons. We can say that texting caused a 20% increase in reaction time because multiplication can meaningfully be carried out because we don't have negative numbers. Yeah, Yonhan gave a great example there of, I think I highlighted that example in last year's QDA class, that you might need a within subjects design if you need a relatively hard to access group of participants. I think a lot of educational studies will sometimes use within subjects designs because it's just tough to get your hands on like a classroom full of kids. So we're using so is this ordinal data or ratio data or what? So we have two variables here. Our measurement of secondary task is is nominal. It's either texting or control. There's no order to them at all. Our measurement of reaction time is ratio. It goes from 0. You could theoretically have a 0 millisecond reaction time. You could have hit the gas right when the light turned green, or you could have had a positive reaction time. You hit the gas a few milliseconds or a few seconds later. And I just want to end on this point because this will lead us right into the practical, that one of the main things we'll want to do once we get our data is to describe that data using descriptive statistics. And probably the most common descriptive statistic we want to describe about our data, the most common trend we would want to describe is the central tendency of that data. The first most basic step in describing a trend is just describing the central trend, describing something common or middle or something descriptive about that data set all in one quick number. This might be a review of school math, so I'll try to keep it simple. I gave a list of numbers up here and we'll compute each of these for that list of numbers. It's a list of 10 digits, 10 numbers. So our first most basic idea of a central tendency is a mode. Modes are useful because they can be applied to any data type. They can be applied to ordinal data, nominal data, ratio, or interval data. You can say that the modal gender in your group of participants was female, that you had more female participants than male participants. Likewise, you can find the mode for a group of numbers. In this case, this sequence of numbers, the modal number is 5 because more 5s appear than anything else. If there's a tie, then you can say that the data is multimodal, that it has more than one mode. while this is a measure of central tendency, it really doesn't tell us, it tells us a little bit about the sequence of numbers. It tells us something that showed up a lot, but it really doesn't tell us where the middle is in any meaningful way. But luckily, we have other measures of central tendency that can give us more information. We could instead use a median. Medians express the central tendency for ordinal, interval, or ratio data. So we can use this for anything ordinal and above or below, or however you think of it. To find the median, you just count how many variables there are, you put them in order, and you pick the middle variable, the middle value. So right here, I have 10 numbers. The middle is between the 5th and the 6th. Luckily, they're both 10, so my median is 10. If we had, for example, a list of how frequently people used an app, we had 3 people that said they're beginners, 1 who said they are experienced, and 4 that said they're experts. Now we don't have a clean middle, we don't have a clean median. We would say that the median value was probably experienced / expert. We wouldn't say like experienced and a half or something like that. But we could still meaningfully talk about a median because there's an order to those, to that data. Notice in this sequence, even though we have one really extreme value, we have that 100, which is really high. That 100 doesn't have any more influence on the median than any other number in the sequence. On the one hand, that means median's a good way of expressing central tendency. It tells us something about the middle. But on the other hand, there's also some information about this data set that the median alone doesn't tell us. We don't know about that 100. We don't know about that extreme value because we used a median, which doesn't get influenced by extreme values. Finally, we have means or averages. These can be used only when we have interval or ratio data. Means, as you might recall, are found by adding up all of our numbers, dividing them by the number of values we had, and finding what that number is. If we add all of these numbers together, we get 200. I already told you there's 10 of these numbers, so the mean of this sequence is 20. Notice that the mean is much higher than the median for this example because there's this one extreme value, there's this 100. Extremes have a much larger effect on means than other values do if the values are closer to the center. So that 100 pulls the mean way up high towards in the direction of 100 instead of being towards that other middle of 10 that the median told us about. Now, it's always good to report both your median and your mean because they tell us, in this case, they gave us some really good information. The median and mean were pretty different. So that tells us both that the center of the data is somewhere in this 10, 20 area, but it also tells us that we probably have some extreme high value that's yanking the mean up higher than the median. Reporting both your median and your mean both give you some description of the central tendency, and reporting them together gives you some added information that you wouldn't get from just knowing one. The median of these numbers is 10 because if you line them up in order, you can basically just cross them off. You cross off the 5 and 100, cross off the 20, 5, cross off that. Eventually, the only 2 things you have left are 10 and 10. And instead of, so since these are interval data or ratio data, since these are numbers, we can just take the average, we can find the middle point, but they're the same number anyway. That number was 10. So the median for this data, for this set of numbers was 10. If you have an odd number of numbers, if your data is an odd number of data points, then the median is really easy to find because there's only one number right in the middle once you line them up in order and start crossing everyone off. If the middle ones were 10 and 20, for instance, then we would just take the average and we would say that the median was 15. That's possible when we have interval or ratio data. If instead we lined up people's ranks, if we lined up, like beginner, expert, and novice, and the middle was somewhere between expert and experienced, for example. In that case, we wouldn't try to take the average of expert and experienced. We would say that the median was experienced / expert, something like that. Just a way to express that the median was in between. Someone was direct messaging me questions. I'm not just talking to myself and responding to the void, though it does seem like that. But that's pretty much it for the lecture on, the scientific method and descriptive statistics and central tendencies. I'll just remind you that the reading for this week, the only reading is the first chapter of the textbook. You'll get a taste of Andy Field's inimitable writing style. It's nothing like most textbooks, for good and for bad. It's fun, and sometimes it's like, please just teach me stats and quit trying to be funny. But you'll grow to love it or hate it. I've also thrown a few papers about texting and driving onto Brightspace, but that's just additional info. If you're interested, you don't need to read that stuff and it won't be involved in any assessment. So that's like just for fun. But that's your reading, and I'll let us take a 10-minute break. Let's meet back up. Let's call it screw it. Let's call it a 10-minute break. I'd rather eat into the practical demonstration than eat into your break. We'll come back at 3:08 by my clock, and we'll work on R. So when we come back, try to have R Studio open and try to have that that folder created that I told you to create. And you can keep any questions coming into chat if they come up during your break. All right, hello, welcome back. Hopefully you've had a chance to create a folder, download those files. And hopefully you have R Studio open, ready to go. If you get a little bit behind, luckily I wrote down lots of instructions in the R file that I made today. So you shouldn't ever get too far behind, but if you ever do need some extra help, feel free to throw comments into chat or to ask me to slow down or go back. So hopefully when you open up R Studio, it will look something like this. It'll probably be a different color because I made mine dark because I stare at my screen all day, and a lot of that involves staring at R Studio. But hopefully it has a window that says console. It may or may not be, it might be taking up the entire side, or there might be another window called source or something else up here. There should be a bottom right area that has things like files, plots, packages, help, etc. And then maybe something up here that says environment, and it might say the environment is empty. So the first thing we might want to do is open that lecture2code.r file. So I have this pleasantly named folder called QDA 2022 inside my folder called R. So I can open up this lecture2code.r, and that'll help me just read the instructions and like see all of the code right here in the script window. So we'll give you a little tour of R. So if you only have the console, then you are probably in R and not in R Studio. So you should have R Studio opened. If you're in R Studio and you don't have the console section, then, and you only have the console, then opening a file should sort you out. But if you have R open, but you don't have R Studio open, you won't have the rest of these pretty little windows. So first of all, you might see everything's not in tidy little lines like I have here. If you want this to look a little nicer, if you go into the code tab and hit soft wrap long lines, that'll make it so everything's more, it fits into the screen better. But first I want to give you just a little tour of what these windows are. So as we saw last week, down here is your console. That's where if I type 2 plus, it's where if I put 2 equals 2, R gets mad at me. But if I put 2 plus 2 and hit enter, it tells me that 2 plus 2 is 4. So this is my console. This is my calculator. This is where all the code actually runs. This is where everything gets, all your code gets evaluated. All your code runs down here. Up here is your script window. So every week I'll be writing one of these .r files. .r files are called R scripts. And all that means is that it's a text file that contains, it can contain plain text. So it can be just things like my instructions where it says, welcome to the first week of coding in R, or it can include things like actual lines of code. The scripts you can also write yourself, and I hope you do, not just rely on my scripts, but also write your own scripts. So yeah, the file is on Brightspace. So the same, it's in the learning materials week 2 or lecture 2 or whatever folder. You'll find lecture2code.r and driving.csv. So hopefully somewhere on, and not on SysWeb though, but on Brightspace itself. So hopefully you can find that. Yeah, download the CSV driving file and throw that into your QDA folder also. So yeah, that's your script area. That's where you can have text or code. You can, anytime you want to make a new script, some people like to follow along by typing their own code and typing their own comments. That will definitely help you learn if you don't want to just rely on my code. So if you click this little new file button up here and hit R script, you'll get a completely blank script. So in a script, you can write things like code. You can write 2 + 2. You can write, if you use that hashtag, you can write comments. So you can write, maybe before I write 2 + 2, I want a comment that says, this is where I check what 2 + 2 is. So that's just a comment. I can't make R run that. That's just a note to myself. You've opened the file, but you don't see my descriptions. The link on Brightspace is lecture 2, code 2. File I'm showing with the descriptions. Might be. Sorry about that. Let me upload the right file real quick. That would help. Sorry. I probably replaced the old file with last year's version where I didn't give all these instructions. So I'm opening Brightspace on the side. Yeah. Sorry. That'll definitely help, huh? Luckily, we have not gotten far. 1 second, just going into Brightspace, a really fun and easy to use virtual learning environment that I'm sure you'll love even more as the year goes on. Make sure lecture2code.r. Yeah, that is that file. So now I can switch this. Change file. Yeah, I put last year's file up there and it doesn't have all my nice fun instructions. So this should help a lot. Now, if you all right, now if you download the file that's just called lecture2code.r, it won't have that extra 2 in parentheses. Download that, throw it in your QDA folder, and either open it in Notepad or open it in R, and that should be a lot more helpful. That'll have all of these instructions like welcome to the first week of coding in R. Anyway, yeah, up here is your script. You can write anything you want up here. It doesn't get evaluated right away when you run it. So I wrote, let's do something else. So I wrote 3 + 3 here, and it noticed that R has not yet checked for me what 3 + 3 is. It just says it in my script, but it hasn't run. To actually run the code, I have to either hit this run button, and when I hit it, it throws my comment and the code there, and 3 + 3 is 6, so that's good. Or I can, on that line that I want to run, I can hit Command Enter or Control Enter. And if I hover over run, I think it'll even tell me, yeah, I'm on a Windows computer, so it says Control Enter to run that line. So I can just have my cursor on the line and hit Control Enter. I can highlight what I want to run and hit Control Enter. I can highlight everything and hit Control Enter. And in any of those cases, whatever I have selected will get run by the console. The calculator part of R will actually check the code that I put in there. So each week I make these code walkthroughs. I make these scripts with lots of notes, lots of instructions and guides for how to actually write this code. And a lot of what I'm writing is just comments. It's just things after a hashtag. That means R is not actually reading it. It's just text for you, the reader. I highly suggest when you write your own code that you write your own comments as well. Now, they don't have to be as wordy and conversational as mine. Mine go really over the top for the purpose of teaching. But you should always at least have comments like this that have a little note explaining what the next line of your code is even trying to do. That way, when someone else reads your code to help you out with it, whether it's someone in your buddy group or someone from the teaching team, we know exactly what you were at least trying to do with your code. So that's the script area, that's the console. This is your files, plots, and packages window. It's kind of the all-in-one. So for me, it's looking in my QDA 2022 folder. It probably isn't looking in that folder for you quite yet. Could you tell me what error you're getting, and we'll see, we'll work through it together. So this is your files, plots, packages, pretty much everything that's not just no data loaded error. I would say try opening it in Notepad, try opening it in whatever kind of plain text viewer you have. Sometimes our studio is a little funky with file encodings for some reason, but hopefully if you open it in Notepad, it'll be there. Or maybe we gave like Brightspace like a hug of death that everyone tried to download at the same time. So yeah, this is where you'll see your files in whatever folder you're telling R to work in. If you make graphs, they'll appear here. If you need help, this is where all of like the extra help is for. Great, I'm glad WordPad is useful for looking at these files too. This is where you can also like look at some of the documentation for R, but this is where a lot of your extra stuff here is. Yeah, so you probably don't have a folder called Justin. So I'm guessing you don't have a folder called Justin. Whatever that file path is, maybe you do have a folder called Justin. I wonder what else is in that folder, but you should adjust that file path to reflect the actual name of where you want your QDA folder to be. Mine is in users, Justin, documents are. Yours is probably somewhere else. Yeah, someone asked, can you show how to make a new untitled screen? So just up here, there's a button for a new script. You just click the new button, hit R script, and you get a new blank script. So I'm going to close my blank script. I'm not going to save it because it's blank. Now I've kind of introduced you to the 4 areas. Oh, you'll never get access to the Justin folder. This is our 4 kind of areas of our R screen. Oh, I didn't talk about the top one. The top one is the environment. This is R's short-term memory, basically. This is everything that R has remembered since the time you've opened it. Now you can change the, you can change from week to week. You can save the short-term memory for next time you open R if you want it to all be in there. Oh yeah, sorry, if it's overrunning, if my comments are too long, if you go up into code and hit soft wrap long lines, it goes from looking like this to looking like that. It'll be a lot prettier for you. Great, I'm glad it's opening in RStudio for you now. I don't know why RStudio is funky with that. But yeah, your environment is your short-term memory. So it'll only remember what you've done since you've opened R this time. When you close RStudio, it will ask you if you want to save your environment. It's not always a good idea to save your environment because eventually you'll have so much stored in your short-term memory that you won't be able to find anything. It'll just be like overwhelming. You can also always, if you have stuff saved in here, you can clean. That's a little broom. It just means empty out your short-term memory, empty out your environment. You can also empty out the console. So if I don't want all this 3 + 3 = 6 garbage, I can just hit this little broom and I cleared my console. Now it's nice and clean. The R script section is useful for helping you save code. So if there's something that I don't want to type again and again, like if I know that I need the command 2 + 2 a lot and I don't want to have to manually type 2 + 2 or hit copy and paste all the time, I can just run that line every time I need it. Now that probably doesn't seem super useful right now, but this next step will make it seem a lot more useful. So each week we're going to want R to look in a specific folder, and my comments kind of tell you this, but we want R to know what folder to look for files in. That folder in R's terminology is called a working directory. So that's the directory, the folder that it's working in. You can set your working directory with this command set wd. I want my working directory to be my folder QDA 2022, which is in a folder called R, which is inside a folder called documents, which is, you get it. I set my working directory like that. You can find what your file path is and change that up so it reflects where your QDA folder is. And now I run that line, and now R is going to be looking for files there when I ask it to do things with files. You'll need to run that line of code every single time you use R. So every single week, you'll want to remind R to look at this. This is my working directory. One useful thing you can do is if you save this script, every week you can just copy and paste this line into your new script, or you can just run this line from this script, and you'll always have your working directory. You'll always have R looking in the right place. If that didn't work, if that line of code couldn't find your working directory, if it said something like that file path can't be found or something like that, or if you're lazy and don't want to do this every time, there are global options. You can also tell RStudio exactly where to look for your working directory by going into Tools and then Global Options. You can then tell R to set something as the default working directory all the time. You can browse through your own file structure, and I'm not going to do that just now, but you can browse through your own files and find where your working directory is in case R didn't find it when you typed it yourself. This is also where you can do things like I did, like changing the appearance to a different color scheme, more zoomed in, different font sizes, different fonts, whatever else you want. You can do that in the appearance section, also in global settings, global options. The file path you need to put down in that line is wherever that folder that you made is. So if you made that folder in your documents folder and your name is not Justin, you probably need to change Justin to whatever your name is, or wherever else. Maybe you made it in your downloads folder and it's like download / whatever. Otherwise, if that's not working as intended, if you can't get R to look at to get that options pop up, just hit tools and global options. And then when you set your working directory that way, you click on your QDA 2022 folder, hit open, hit apply. Then that should become your working directory. You can then also over here in that more in your files, just hit go to working directory. And then whatever you set in that global options will be where R goes to. So hopefully, if you were able to do that, if you're able to set your working directory and get R to navigate to it, you should see in your working directory a file called driving.csv, and probably this file, this lecture2code.r. Error in set working directory, cannot change working directory. I would say try your global options, so try it this way and see if that worked. If not, I would say try opening RStudio like as an administrator with, with higher privileges or whatever. Okay. So if you got that working, if you now see your driving.csv file, that is the file we will want to work with today. And every single week, I'll be giving you some data file that you'll be working off of. It's always going to be a CSV file. CSV files are like Excel files meets text files. It saves like sometimes R can crash, and it's free and open source, and we're thankful that R exists and that RStudio exists, even if it's not always the best program. So hopefully when you open it back up, it will have that working. Open permission denied. So permission denied stuff definitely sounds like you need to elevate your privileges. You need to open RStudio as an administrator or change some kind of administrative or security settings on your computer when opening R. That I leave to the reader to solve as an exercise on their own. But yeah, each week I'll give you a CSV file. CSV files are essentially Excel tables or Excel spreadsheets, but formatted as a text document. So you could open your CSV files in WordPad or a Notepad or anything like that. Likewise, you can open them in R or open them in Excel, and no matter where you open it,